shop lit where the circuits gleam. Ale's got the tools, living the dream. Some things blow up, oh yeah, it's true. But it's all part of the fun when I'm sharing with you. Amp it up, let the music flow. Ale's got the magic, come and see the show. Experimenting with wires, making sound divine. When things blow up, we just laugh, that's fine.
Greetings, the Astro 30 here yet again, and welcome back to AEL. Now, if you're new to this channel, please consider going down below and subscribing if you haven't done so already. That'd be great, thanks. Today I'm going to look at a circuit I found randomly online. I was looking for another type of power amplifier and this popped up. It's actually a 5-watt amplifier. However, the name of this file is a 3-watt amp PNG. So yeah, okay, there is a discrepancy there. This is a quasi-complimentary output stage formed by T3, T5, T4 and T6 respectively. And what that is basically one side of the amplifier is in Darlington configuration, whereas the other side, the negative going cycle part, is in C clay E. And both output transistors are the same polarity, in this case MPN. Now, a lot of amplifiers have been built using this type of topology. In fact, a lot of integrated circuit amplifiers use MPNs as the output stage in this common configuration of quasi-complementary. R7 and R8 here, these two 56 ohm resistors, are chosen so that the output stage is either barely on or just at cutoff. It's self-biased with this 33 ohm resistor D1 and D2. To increase the gain of the amplifier, you could reduce the value of R4, but it's not recommended because it may cause the circuit to become unstable and prone to oscillate. These degeneration resistors I'm going to change to 0.22 because, well, I don't know of any resistor value that's 0.2 on its own. In fact, in the testing rig I'm probably going to use 0.33 because that's what I have to hand. C3, this one here. C5, which is, if I can find it, there. C6, which is up here. Plus R3, which is, I can't see it, there. Just ensures stability of the amplifier so it doesn't go into oscillation. And this resistor 4K7 here is also basically a stopper resistor for the base of this direct coupled voltage amplifier. And that's basically the whole entire circuit. We have a bit of local feedback, negative feedback via this 4K7 resistor here back to the emitter of the first input transistor T1. There's not much more to talk about this circuit, so what I'm going to do is I'm going to build it up to the output stage but not include the output stage, and I'm going to test the output here, well actually here at the capacitor. There's different values of capacitors here on the output one that you can use for 4700, which is quite a large capacitance. He's chosen for 4 ohm loads, and if you use an 8 ohm loads, 2200 will do just fine. So as I say, I'll test this up without the output stage connected because these two transistors will form the output, but when you load the amplifier it's not going to be very happy with you, put it that way. Because these transistors, which are BC547, this one's not marked, but it'd be 557, aren't good at driving, you know, low impedance loads like a loudspeaker. As for the output stage transistors, these are 2N1613s, which are one of those like CAN style old school transistors, which you can barely get nowadays anyway. I don't have them, so for my testing purposes I'm going to use TIP35C for both. And once I've tested that the amplifier actually passes a signal unloaded, I will then include the output stage and then test the amplifier loaded at various different voltages. I'm going to start it as 12 volts, then I'm going to test it at 17 volts, then I'm going to up it to 24 volts, just for shits and giggles. Anyway, let's get started with building the circuit up on breadboard. Well, a short time later I've got the circuit built. It's spread out quite across most of the breadboard here. It doesn't have to be, but it was a lot easier to fault find, and I have actually got it producing an output now. I did have the collector of this transistor here, which is one of the drivers, connected to the negative rail instead of the positive rail. The same was also true for one of the PNP transistor in the direct coupled voltage amplifier down here. It was also going to the negative rail instead of the positive, so I was getting no output. Okay, I got my power supply set to 12 volts initially with an 800 mA current limit. And, well, we're drawing all of about 5 mA at the moment. There is a green LED up here which is indicating that it's powered to the circuit, so that is drawing most of the current at the moment. So I'll connect the oscilloscope up to the output capacitor and ground. And unloaded, we are seeing an output signal, so I'll just drop it out of clipping. So it's out of clipping now, and we're at 1 kilohertz. That's a bit better. 1 kilohertz, 3.7879 volt RMS in a times 10 probe. So the little circuit is working just on the drivers alone, as I said it would. And the signal is varying up and down with the oscillator amplitude, which is, well, what it's supposed to do. So the next thing to do is to build the output stage and actually load it into the dummy load, which is sitting off to the right there, and actually see if this works as a power amplifier and what sort of output we're getting. Output stage is built, and I've got it on this aluminium stock, 2 TIP 35Cs. The generation resistors, which are actually 0.33 ohm, soldered where they need to be in the circuit with some fly wires attached to it. Now all I've got to do is attach it to the circuit. Output stage is connected to where it needs to be connected, and we are into the dummy load. So I'll increase the gain till it clips, which is there. So I'm going to say about there maybe. I need to increase that a bit so I can see it. Drop it off. Yeah, it's not very stable, but that's 2.8, I'm going to say, volts RMS, which is only 980 milliwatts. However, it could have something to do with my choice of output transistor too, but anyway, I wasn't expecting much power at 12 volts. So now what I'm going to do is I'm going to take these measurements again off camera into the various different loads, 8 and 4, 12, 17 and 24 volts, and I'll compile a list of my results and come back with those findings in just a moment. Okay, and a short time later I've come back with my results of power measurements. Now we already knew at 12 volt into 8 ohm it produced 980 milliwatts. And at 12 volts into 4 ohms, I'm actually getting 1.5 watts, which is nice. 17 volts, the predicted maximum voltage of the original circuit, into 8 ohms produces 2.7 watts, so it's probably more closer to the 3 watt amplifier as the image file name is called, rather than what the text is called. At 4 ohms at 17 volts, we're getting 3.4 watts. Nice. Finally, at 24 volts into 8 ohms, we're getting a massive 5.7 watts. Nice. And into 4 we're getting 8 watts. So as we can see, we are getting a little bit more power into 4 ohms, but we're more around the 5 watt mark at 24 volt DC. However, I wouldn't go any further than 24 volt DC unless you're going to change all the small signal transistors to something a little bit more beefier. And I also went ahead and measured the currents at those loads and voltages. So the quiescent current with the power amplifier loaded, and this is at 24 volts by the way, we're around about 16 milliamps. With the amplifier unloaded, i.e. not connected to a speaker, we've got 7 mA. So the quiescent current is around about 7 mA. And I've removed the LED whilst doing this test. So at 12 volts into 8 ohms, we're getting 108 mA current draw, which is 1.2 watts of dissipation. Into 4 ohms at 12 volts, 275 milliamps at 3.3 watts dissipation. 17 volts into 8 ohms, we're getting 262 milliamp current draw, 4.4 watts. Into 4 ohms and 17 volts, 409 milliamps and 6.9 watts of dissipation. And finally at 24 volts into 8 ohms, it's 382 milliamps of current draw at 9.1 watts. And at the 4 ohm one, we're getting 616 milliamps current draw at 14.8 watts dissipation. So I guess the next thing I should do is I want to see what the input sensitivity is to this amplifier. I'm going to use the 24 volt because that's the final voltage I want to run this at anyway, is 24 volts. Now currently we're clipping a bit, so I'll back that off till we're no longer clipping. There we go. And all I have to do is just move my probes. So I'll disconnect the probe from the load, and I'll now connect the probe to where the input comes in and a suitable ground. There we go. So we just increase that so we can see it. Yeah, it's moving around a bit. 489 millivolt, 489 millivolt RMS. So yeah, about 489 millivolt RMS in equals the what is it? It's 5.7 watts out. Okay, so I'll switch this back to the output, and I was thinking I won't do a frequency response test on this because, well, it's on breadboard, and breadboard's not a good base for amplifiers because of all the extra capacitance the connections have. But I'm going to do it anyway. I've just noticed something interesting. With the input disconnected, looks like we're picking up a bit of radio frequency. Because if I now move my hand close to the circuit and release it, it goes away and comes back. And that's me touching the input. Interesting. I'm going to use an online sweep generator for this because I don't actually have a physical one. So this is only as good as the frequency response of the computer's output on the headphone socket. So you've got to take that into account. So this is only just a raw measurement. So currently I've got the start frequency and the end frequency both the same. This is just so I can get a baseline reading on my scope. And by that I mean so I can get the trace to go in between two of these gradicules. So we've got like two gradicules on the screen taking up the whole entire waveform, so we can see if the voltage changes. You can look at the scope screen, here we go. Not sure why it's bouncing around like that, but it's reasonably flat up until 11 kilohertz. So I'm going to change my frequencies to 10 kilohertz each. Now, did you notice that when I started, there was that increase in volume and then it dropped off? It's most likely the output capacitor discharging into the load. So we're losing a bit of voltage at 10 kilohertz. So I'll change it by half to 5 kilohertz. And we will see. Okay, so I've lost a bit of voltage there as well. So I'll go back to my base frequency, which was 1 kilohertz. Since turn base. So now I'll do a small sweep between 1 and 3 kilohertz. That is weird, but the voltage is dropping off, so it's starting to roll off at about 1.5 kilohertz. But why it's doing that, growing and shrinking, I don't know. And the power supply is bouncing around all over the place too. Okay, so the little circuit does work, but it's doing some weird voltage up and down on the scope when the frequency is sweeping. That could be its design, or it could be this output capacitor, as I said, just discharging. Yeah, it's unknown at this point. It could be a combination of layout and the capacitor. Anyway, this is why I said doing a frequency response on a breadboard design is not really a good idea. So what's next? Well, I think what we should do is hook it up to a speaker and just hear with the sweep whether or not the volume is perceived to be changing in loudness. So that's what I'm going to do next. Alright, I've got a US audio speaker connected to it, 6 ohm, little 5-inch job I believe they are. Okay. It's a fairly old speaker. It's perfect for testing anyway, because my other speakers are connected to my test amp now, so I don't really want to go messing around disconnecting them. So I'm going to turn the power on, and we're going to listen to see if we hear any unusual noise come out the speaker. Nothing. I can hear some noise coming from the computer's audio processing chip, because we shouldn't be actually producing any output at the moment because I turned it off. Anyway, there's a slight little thump there when it turned on, but other than that I can't hear anything other than that noise sine wave coming from somewhere. So I don't know how loud this is going to be, so I'll just start the sweep. That is way too loud. So I'll drop that down. It's got a very harsh sort of distortion there. That could be the breadboard. Anyway. Now, I can hear audibly what it was doing on the scope. If I close this tab, in fact, no, it still seems to be trying to produce the sound. I'll close the browser. No, in fact, it's still there. So, alright, what I'm going to do now is I'm going to reboot the machine, which is still there. The input's disconnected. There's that noise that I was seeing on the scope before too. But interestingly, the circuit seems to be producing a 1 kHz sine wave by itself. Alright then. Alright, let's just play some audio and see how it sounds.
Stepping out of my door, feeling kinda bold. Got a curious mind, let the story unfold. As I groove to the rhythm with the sway and a twirl. There's a question on my lips, let it dance in the world. Is it earth or a potato, can't you see? Round and earthy, they're both part of the spree. But hold up now, we gotta clear the fog. Flat earth is trying to logic like a lost stray dog. Is it dirt or a potato? Hey, let's groove. Spinning circles, doing the physics way. Looking up at the stars, can't find the way. Talking about gravity like it's child's play. Hey buddy, you're missing all the laws in the jam. Misunderstanding physics, living life in a scam. Spuds in the field, they know the score. Earth's a spinning ball, who could ask for more? But the flat earth crowd's still stuck in the spin. Catching phony vibes, oh where to begin? Is it duck or a potato? Hey, let's groove. Spinning circles, doing the physics move. Ain't no grifter gonna pull the wool today. Just alive to jam, come on, let's sway. Oh, the world is round, can't you see? But up in the clouds, there's a fantasy. With every conspiracy, they dance on the edge. Like a twirling dervish, they pledge and dredge. What's real and what's fake? They muddle it all. But we're here, grooving, ready for the ball. So let's lift the vibes, break free, shine bright. Together we'll dance till we're lost in the night.
Okay, that's going to annoy a few flat earthers, but anyway, it works. There does seem to be a background distortion there, and I'm not sure why it's distorting like that. It could be my computer's sound chip. I've had issues with that in the past before. And where that 1 kilohertz oscillation is coming from, I do not know. It doesn't show up on the scope in any way. Not as far as I know. So, yeah, that's what we've got. What's next for this is I'll design a printed circuit board so I can actually test this properly, like do a proper frequency response test. I might have to do it the hard way with the oscillator and set it at predetermined frequencies along the way, like start at 10 Hertz, jump to 100, jump to 200, and so on and so forth exponentially like that, and just plot it out on a graph. Also want to see if that annoying 1 kilohertz background tone disappears, and whether the RF interference pickup at the input here also disappears, because, well, I've basically got all this exposed wiring, which are all acting like antennas anyway, so there is that. Now, there's a couple of things I forgot to mention with this schematic in the intro there. First of all, the first input transistor here is biased at the halfway supply voltage point by these two 100k resistors forming a resistive divider, and the input comes in at the center point. So this input stage voltage amplifier here is operating in class A. The other thing I don't think I mentioned was this extra 1k resistor here going between the output and the ground, basically across the speaker. What this does is provide a discharge path for this capacitor, so if you don't have a speaker load connected and you suddenly connect the speaker load to it, if it's turned on, it's not going to produce a huge pop through the speaker as this capacitor discharges all its current through the driver. So there's that. And quite honestly, this looks like very much like a Douglas Self design. It's very Douglas Self-esque, in my opinion. It probably actually is. So that's it. That's going to do it for this video, and I hope you enjoyed it. Yeah, I'm not sure where that distortion's coming from, but again, breadboard is not a good medium for building power amplifiers. Never was. But it's a good medium to test to see if the circuit actually works. And then the next step in that is you should really prototype board it out, like on Breadboard or stripboard, something like that, so you can work out all the problems and then have a PCB made. Considering the PCBs are cheap to make, under 100mm square, only $5 American, which is about, I think, $9 AU, something like that, plus the shipping. It's not that expensive to have one made. So that's the next step, is to make a PCB for it and see how well it works on a PCB. I'm wondering if I should change the output transistors to TIP41C, something like that, instead of those large TIP35C transistors in the 218 package because, well, it's off, but they don't dissipate that much heat in this circuit, so it seems like overkill to have that size of a transistor, but anyway, leave your thoughts below. Anyways, this is the Astro 30 saying thank you for watching. Hope you enjoyed it. If you did, please remember to go down below, like, comment and subscribe if you haven't done so already. And as always, this is the Astro 30 saying see ya, have a great day. See you in the next one. Cheers.
Amp it up, let the music flow. Ale's got the magic, come and see the show. Experimenting with wires, making sound divine. When things blow up, we just laugh, that's fine.